does speed matter? Well, it can mean the difference between a ticket and being late by several minutes. It can also mean the difference between a successful launch and a product failure. You see, speed is not just a measure of time. It can be an important multiplier for other efforts. Faster execution leads to better customer outcomes, which leads to greater internal efficiency and ultimately superior financial performance and sustained growth. So, when it comes to our FPGA based prototyping, how do we speed up our design process? With the help of Siemens Veloce proFPGA CS. That's how. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, Ludovic Jacomme from Siemens and I investigate the benefits that Siemens Veloce proFPGA CS platform can bring to your next FPGA-based prototyping project, and how you can take advantage of this solution today. And before we get started, don't forget to click that link. There you can find even more information about this topic from Siemens. Hi, Ludo. Thank you so much for joining me.
Thank you.
All right, so we're talking about FPGA-based prototyping with the latest high-capacity FPGA that can enable new use models. So, Ludo, before we dig into the details, what are the biggest challenges you're seeing in this space?
When we are talking about chip design, SoC, and IP development, the software parts is becoming increasingly predominant. And the differentiation against a competitive product is more about the software, much less about the hardware itself. The software workloads really explode in terms of complexity, given the number of CPU cores, interacting with graphics, AI algorithms, running sometimes multiple OS. System itself should have the best performance to run that complex software with minimum power consumption. The other challenges that the designers are facing is to shift left in the development process. So all about shift left, it means to develop, to run, and to test the software as early as possible in the development flow for the entire system. And to implement that shift left methodology, you need to be able to run the production system software on a non-existing chip and non-existing hardware, which of course is clearly a challenge. And the solution that exists for this challenge is then to use an environment that lets you to implement and to execute cycle-accurate models of your hardware, running your firmware or operating system-level software, while your chip and your hardware don't even exist yet.
So, Ludo, these kinds of challenges can be very expensive, right?
Yeah. If you look at the cost of a chip design, the part of the software in green on the chart on the right is really predominant. And it is increasing with the complexity and the density. What we are seeing those days, yes, in 5 nanometers or even deeper technology, it's really increasing. If you can see the curve, it's close to be exponential curves. So another aspect that drives the shift left requirements is the cost of software bugs. And this is what you can see on the chart on the bottom right. The later bugs you are discovered and exposed, the higher is the cost to fix them. And the worst scenario, of course, is when they are exposed when the software releases out and in production at customers. It's really the nightmare. So imagine a platform that lets you to get a much better coverage at RTL design stages and to identify bugs much earlier and to fix them accordingly. And the solution is FPGA-based prototyping, used at the early stage of development process while running very large software workloads on cycle-accurate RTL models, executing astronomical number of cycles at multi-megahertz speed.
So, Ludo, I understand that FPGA-based prototyping is really about speed, but how do you reach the best performance?
So that's a very good question. So FPGA-based prototyping is first about hardware. You need to have the best FPGA available on the market, addressing both performance and capacity targets. The highest performance is generally achieved as soon as you succeed to put the most critical part of your design, for example, a CPU core, in one single FPGA. You can see on the right the largest FPGA available on the market, VP1902 from AMD. And of course, it is used in our FPGA-based prototyping platform, proFPGA CS. Then comes the cabling flexibility and number of connectors that will be used to interconnect the different portions of your design on the multi-FPGA platforms. With very flexible cabling, you can implement on the prototyping hardware a perfect mapping of your design's topologies, leading to a much better performance. And the performance of the connectivity is also a key aspect, especially for the design that have strongly connected components or large buses, for example, and by, I would say, connectivity between the different parts. You can see two flavors of our FPGA-based prototyping platform with a desktop version of our Exablade. This is a 6 FPGA-based platform. So you have the desktop version. You have also the rackable server version with multiple proFPGA CS blades, and you can reach up to 10 blades and even more in the future. FPGA-based prototyping is also about software. So to automatically compile the user design from RTL to FPGA bit streams. And to achieve the best performance, there are key components provided with our compiler. We call it VPS. Okay, so VPS stands for Veloce Prototyping System. And first, you need to have timing-driven and timing awareness at every level of the compilation flow. It starts with the proper identification of clocks and their automatic transformation to have an equivalent scheme, FPGA-friendly, since generally the design we are compiling are ASIC designs, and the ASIC clock schemes are not compliant at all with FPGA structure. So this is where we need to have some automation. And it's then about RTL synthesis, memory, and DSP inferences, focusing on reducing the logic depth for the most critical path of the design. And finally, the FPGA partitioning and optimization on logic replication algorithms to get the best performance for multiple FPGA designs. And once the design has been compiled, the user will get out-of-the-box performance. That's really the goal and what you can obtain with VPS. Now, it may happen that the out-of-the-box performance is not good enough. If it is not meeting the target, we are providing some methodologies to improve further, to fine-tune the performance at different levels of the flow. And a set of tools are provided to analyze and to refine the partitioning, routing, in order to push further the performance while adding extra constraints and timing exceptions, for example.
So, Ludo, can you provide some more details on the different steps of the VPS compiler?
Sure. So in the past, for small designs, all those steps were done manually by the designer. But on large SoC, that is not necessarily achievable, not in a timely manner anyway. So to implement the user RTL design on the FPGA, the VPS compiler is going through multiple steps to automatically, let's say, massage the RTL of the design, taking care of ASIC-specific schemes, such as multiple drivers, high states, gated clocks, etc. And the netlist is optimized to use as few as possible FPGA resources, while also at the same time having the best performance. So critical steps for performance, such as I/O cut between FPGAs, optimization of routing between FPGAs, and pin muxing implementation that is done using some timing-driven algorithms.
Okay, so are there any interactive GUI to help the user compile their design?
Yes, VPS is coming with a main cockpit called Build Assistant that is used to guide the user to set up its prototype project and to let him to go through the different steps of the compilation. So at each step, there are dedicated GUI widgets that to efficiently monitor and to look at the results of the compilation, to highlight hotspots, to look at critical performance bottlenecks.
So, Ludo, clock identification is a critical step in the FPGA-based prototyping to get good performance. So, how can you help the user with that step?
So to help the user to provide the best input for the clock identification, that is, as you mentioned, pretty critical, we are providing a GUI that lets the user to go over the different clock cones of their design to easily browse the underlying cone of logic. The user is then able to identify proper complex clock structures, to go through them at netlist level using some netlist browser and exploration capability, and finally to define constraints that will help the tool to segregate between clocks, data, and enables, which is the main aspect of the clock transformation.
So, how do you refine the partitioning solution if the solution generated is not meeting some criteria?
That's also one important step. So sometimes our customers would like to do things a bit to refine, I would say, the result manually in order to obtain even better performance. So the VPS is providing a tool to visualize the partitioning result and with different level of abstractions, because you don't necessarily to partition at very lookup tables things. You would like generally to stay at high level of hierarchy. So there are different levels of abstractions provided by the tool. And then it's up to the user to refine the partitioning result and to save the result. It can apply as a user constraint for the rest of the flow. The tool is really to look at what the compiler has achieved automatically and to refine that using the GUI, to reinject some new constraints to the compiler and to review the generated result and to see how it has improved. The user has multiple views, so of course it's original RTL view, the implementation netlist that has been tech map by the compiler, the hardware topology, of course, because here it's really the goal to map the user design to some hardware, and the partitioning that has been generated by the compiler. So while moving from one view to the other, the user can identify what could be done in a better way based on his own set of constraints.
So, Ludo, what do you think is the best methodology to get the best performance?
So the regular methodology to get the best performance is to run the flow without any constraints to see where do we stand in terms of performance out of the box. So that's really the first step. And then using the different tools provided by VPS, the user can look at the bottleneck, especially using our interactive timing analysis engine that will let the user to identify where are the bottlenecks in terms of performance, where are the critical paths, from which FPGA to which one, from which portion of logic to which one. And then looking at the most critical path, the user can get back to the partitioning or to the router and to provide extra constraints or guidance to the tool to achieve even better results.
So, what kind of results are we seeing with the Veloce Pro FPGA CS?
So in the table, you can see the experimental results we have collected. Those are customer designs we have compiled. So with different flavors of hardware. So we have a VU440 FPGA-based prototyping solution, VU19P, and the most recent version, which is VP1902 in proFPGA CS. So what we're seeing is the results in terms of performance depend on the type of the design. For example, there is a clear distinction between CPU and GPU. GPU designs have generally many register barriers and pipelines with small logic depths in between, so it's generally easier to reach good performance, which for CPU is a bit more challenging. And the best results are seen with single FPGA, of course, on GPU design. And for multiple FPGA CPU design, the performance, of course, is a bit more challenging, but we are still seeing some pretty good results. That said, if we compare to the previous generation FPGA-based prototyping platforms based on VU440 or VU19P, we are seeing up to 8x performance improvement on a proFPGA CS platform, which is quite significant.
Well, Ludo, I think that's all I have time for today. Thank you so much for joining me.
Thank you, Amelia.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Siemens. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EE Journal.